We're tackling a common machine learning challenge: overfitting. Our model, an ExtraTreesRegressor, performs great on the training data, high R-squared, but poorly on new, unseen data. This means it's memorized the training data too well, rather than learning the underlying patterns. I'll help you understand how to fix this. The model has a high R-squared score on its training data, indicating a good fit. However, it generalizes poorly to new data. This is a classic sign of overfitting. We'll explore adjustments to improve the model's predictive capability on unseen data. Increasing max_depth lets each tree grow taller, making the model more complex. This often leads to overfitting because the model captures too much noise in the training data, reducing its ability to predict accurately on new data. This is not what we want. Decreasing min_samples_leaf allows smaller leaves on the decision trees. This also increases model complexity and makes it more susceptible to overfitting. We want to avoid this too. By increasing min_samples_split you require more data points before a branch can split. This makes the trees simpler, less prone to overfitting, and therefore more likely to generalize well to unseen data. This is a good approach. Increasing the number of estimators, decision trees, in the ExtraTreesRegressor averages the predictions of multiple trees. This reduces the impact of any individual tree's bias and tends to improve the model's overall accuracy and generalization. This is a great idea. The question asks to identify strategies to improve the model's performance on new, unseen data. The key is to reduce overfitting. We're looking for adjustments that create a more robust and generalized prediction model. I see the core problem is overfitting. That means the ExtraTreesRegressor model, a type of machine learning model that uses many decision trees, is too closely tied to the training data and doesn't generalize well to new, unseen data. It's like memorizing the answers to a test instead of understanding the concepts. You'll do great on that specific test, but you'll likely struggle with a different one covering similar topics. I notice you get a high R-squared value on training data. This is great. But, the problem lies in the poor performance on unseen data. This signals that we need to focus on improving the model's ability to generalize to new information that it hasn't encountered before. This tells me the model is too complex and is likely overfitting. We want to find solutions to address this overfitting and improve the model's ability to generalize. That's where hyperparameter tuning comes in handy. We'll look at how adjusting certain settings in the model can help it to better predict on unseen data. And I need to focus on options that simplify the model. I'd increase the number of trees, estimators. More trees usually improve the model's overall performance by averaging out individual trees' errors, leading to a better generalization, similar to getting multiple opinions before making a big decision. Increasing max_depth will allow trees to grow deeper and potentially overfit the data more. This is generally not a good approach for reducing overfitting. It's like giving the model more power, allowing it to get lost in the details of the training data, and perform poorly on fresh data. Decreasing min_samples_leaf makes the model more complex. Each leaf node in a tree can have fewer samples. This would cause the model to be more sensitive to the noise in the training data. This is another way of saying that I will overfit the data more. I think increasing the min_samples_split parameter is a good choice. This forces the model to create simpler trees, less likely to overfit. Each node needs more samples to split. It's like needing stronger evidence before making a decision. You reduce the chance of making hasty conclusions, and improve generalization. We're trying to make an ExtraTreesRegressor model, which is a type of machine learning model, better at predicting house prices on new, unseen data. It's currently overfitting, doing great on the data it's trained on but poorly on new data. We'll explore ways to improve this generalization ability. The model has a high R-squared score on the training data. That sounds good, right? It means the model fits the training data very well. However, it performs poorly on unseen data. This tells me the model has memorized the training data too well, including its noise, instead of learning the underlying patterns that generalize to new data. It's a classic case of overfitting. I want you to select the actions that can improve model performance on data the model hasn't seen before. We're looking for ways to improve the model's ability to generalize. Increasing the number of trees in the ExtraTreesRegressor ensemble improves the model's stability and reduces overfitting. Think of it like this. Each tree is a single vote. More trees mean a more robust average of predictions, reducing the chance that one single noisy tree dramatically influences the result. Increasing the maximum depth of each tree allows them to grow larger and more complex. This increases the risk of overfitting the training data. Lowering the minimum number of samples required to form a leaf node allows for more complex trees. That makes the model potentially more susceptible to overfitting because tiny variations in the training data can have a big impact on the model's structure. By increasing the minimum number of samples required to split a node, I'm forcing the trees to be less complex and thus less likely to overfit. It makes the decision-making process for each tree more robust. Let's tackle how to improve the generalization of an ExtraTreesRegressor model. We're aiming to make sure our model performs well not just on the data it's trained on, but also on new, unseen data. This is crucial for real-world applications. This tells me the model has learned the training data too well, including its noise. It's overfitting. It's like memorizing the answers to a test instead of understanding the material. You'll ace the practice test but bomb the real one. We need to adjust the model to generalize better. I want to select the options that will improve the model's ability to handle new data and reduce overfitting. This involves understanding how changing certain parameters affects how our model learns. By increasing the number of trees in the forest, we improve the model's stability and reduce overfitting. It's like getting multiple opinions on a house's value before making a decision. The average is more reliable than a single opinion. More trees average out individual biases, making the overall prediction more robust. Increasing max_depth lets each tree grow deeper, potentially leading to overfitting. That's bad. A deeper tree can capture more noise from the training data and perform poorly on new data. Think of it like overanalyzing a small detail and ignoring the bigger picture. Reducing min_samples_leaf lets trees make decisions based on fewer samples. This increases the model's complexity and makes it prone to overfitting. It's like basing a house's price on a few examples without considering the overall market conditions. Increasing min_samples_split means that we need more data before splitting a tree's branch, leading to simpler trees. Simpler trees are less likely to overfit. Think of it as simplifying the problem to focus only on the most important factors. We're tackling how to improve the performance of an ExtraTreesRegressor model, a type of machine learning model that predicts a continuous value, like house prices, using multiple decision trees. The goal is to make the model better at predicting new, unseen data. That is, we want to reduce the model's generalization error. The model performs very well on the data it was trained on, high R². A measure of how well the model fits the training data. However, it performs poorly on new, unseen data. This means the model overfits. I think of it like a student who memorizes answers for a specific test but can't apply the knowledge to similar problems. This parameter controls how many data points a tree node needs before it can split into two child nodes. I increase it to create simpler trees, reducing the risk of overfitting and improving generalization. Think of it as making the student focus on understanding the underlying concepts instead of memorizing everything. This parameter determines how many data points, at minimum, must be present for a node to become a leaf node in a decision tree. I'm decreasing it, which makes the trees more complex and sensitive to the training data. This can lead to overfitting. It's like letting the student focus on very small details that aren't actually important for the overall understanding. The max_depth parameter controls the maximum depth of each decision tree in the model. Increasing this value lets trees grow deeper, allowing for more complex models that can overfit the training data. Think of it as letting the student build a very tall and narrow tower of knowledge which might be unstable and collapse under the weight of unseen data. Estimators refer to the individual trees in the ExtraTreesRegressor model. Increasing their number usually improves generalization by averaging out individual tree biases and reducing the overall model variance. It's like having multiple students answer the test, and taking the average of their answers for a more robust and reliable solution. We're tackling how to make an ExtraTreesRegressor model, a type of machine learning model that uses lots of decision trees, perform better on new, unseen data. It's currently overfitting, meaning it's too focused on the training data and doesn't generalize well. The model is amazingly accurate on the data it's trained on, high R-squared, but fails miserably when we give it new data. This is a classic sign of overfitting. Increasing max_depth lets each tree grow taller, making it more complex. This is a bad idea. Because it increases overfitting, it learns the quirks of the training data too well. Think of it like memorizing instead of understanding. Lowering min_samples_leaf means that a tree's branch can end with just a few data points. This also increases complexity, and is likely to overfit. It's like focusing too much on tiny details and missing the bigger picture. Increasing min_samples_split means that a branch will only split if there are enough data points. This simplifies the trees, making them less prone to overfitting and improving the model's generalization on unseen data. It's like focusing on the main ideas and not getting bogged down in the minor details. Increasing the number of trees, estimators in our forest averages out the individual trees' errors. This generally improves the model by reducing overfitting and improving generalization. Think of it like getting many opinions and averaging them out for a better result. This problem focuses on improving the generalization ability of an ExtraTreesRegressor model. I'll explain how to tune the hyperparameters to avoid overfitting, which means making sure the model performs well not just on data it's already seen, but also on new, unseen data. We're dealing with an ExtraTreesRegressor model, a type of ensemble learning model using multiple decision trees, that shows great performance on the training data, high R-squared, but poorly predicts new, unseen data. This is a classic overfitting issue. Let's explore several approaches to fix the problem. Adjusting the number of trees, tweaking the depth of each tree, changing the minimum number of samples needed to create a leaf node, and modifying the minimum number of samples needed to split a node. The core issue is overfitting. The model is too closely tied to the training data, picking up on noise and peculiarities that don't represent the broader trends in the data. We need to find solutions to simplify the model and improve its generalization capabilities. By increasing the number of trees, I'm creating a more robust model that can better average out the variations and idiosyncrasies of individual trees, making it more reliable on unseen data. Increasing the maximum depth makes each tree more complex. This risks overfitting, because very deep trees might capture random noise present in the training data and struggle to generalize to new examples. This allows leaf nodes to be created with fewer samples. This can lead to more complex trees and worsen overfitting. As the model becomes highly specialized to the training data, it won't transfer well to unseen data. This increases the number of samples needed to split a node, forcing the trees to be less complex and less prone to overfitting. This is a good approach to improve generalization, because it reduces the model's sensitivity to the noise in the training data.